the 2.3 molar mass self-test at the back of our 2.3 molar mass notes. Now, molar mass is a really big idea. I would say it really kind of helps to unlock chemistry for us. And so this is not the sort of concept that if it's challenging to you, we should maybe ignore or try and rush through to get to the answers. We want to really kind of slow down and make sure we've sort of processed and understood what's being asked to the best of our ability. So with that in mind, we're going to maybe try and go a little slow through these and maybe plan through them. And if you feel like it's going too slow, obviously you can just scrub through until you find there's a satisfactory answer. All right, so question one, very simple, straightforward question. What is the molar mass of glucose, which has a molecular formula of C6H12O6? All right, now, a couple of thoughts here. First is that we're told that glucose has 6 carbon atoms. We're told it has 12 H for hydrogen atoms and 6 oxygen atoms. Okay, and in a way, I'm kind of doing a listing givens here. These are given. We're told that glucose has 6 carbons, 12 hydrogens, and 6 oxygens. And we're also told something else. I guess we're told a few other things. We're told that we know the molar mass of carbon. We know how much a mole of carbon weighs. So we got to remember, if we're talking about molar mass, we really want to picture like a scale that is measuring, this is an amazing diagram of a scale that I'm drawing, 10 out of 10. And so there's some readout, right? And here's a little mole on here. I don't know really how to draw a mole. I think they have snouts, maybe. Put some whiskers on there. Maybe nobody will know the difference. And I don't know, it's got like a bulbous body and some legs. Excellent. All right, so that's one mole, which is like a handful of things, right? And we want to know, what does it weigh? What's the mass? This is the molar mass. It's measured in grams per mole. How much does 1 mole weigh? Okay, so to do that, we gotta know that we're told some information on our periodic table. For instance, we're told, well, if we have 6 carbon atoms, we're also told that carbon has a molar mass. 1 mole of carbon weighs 12 grams. So we also know let's say carbon has a molar mass of 12.0 grams for every mole. And we can also read off of our periodic table that hydrogen has a molar mass of, where was hydrogen? It's over here. And we can see it has a molar mass of 1.0 grams per mole. Of course, this is 1.0 atomic mass units, but they happen to convert directly into grams. And that's what a mole is, really. That's why mole is such a crazy conversion factor. 1.0 times, so the molar mass is 1.0 grams per mole. And then lastly, we know that oxygen has a molar mass of, you can find it on your periodic table yourself, 16.0 grams per mole. Okay, and so what do we do in this situation? Well, glucose is quite a complex molecule relative to some of the examples we did in the in the notes. However, in class, we have done questions, we're finding molar mass of things like glucose. In fact, we did one for sucrose. And so if you missed that class, well, that's really why I make videos like this. Okay, so to do this, we're going to have to say, okay, we'll need 6 carbons. So that's going to be 6 times 12.0 grams per mole, and that's going to be equal to 72.0 grams. per mole. Now I also know there are 12 hydrogens. And so that means I'm going to have 12 times 1.0 grams per mole, which is going to give me, so when I put that into a calculator, it gives me 12. And that is how many sig figs I'm going to have. I'm actually just going to have 12 grams per mole from the hydrogens there. Because there are 2 sig figs with the molar mass of hydrogen. This is 2 sig figs there. And this is a counted number, 12. There are exactly 12 hydrogens in one glucose. If there is any more or any fewer, it would not be glucose, it would be something else. And similarly here, we have 3 sig figs. Does the red even show up? A little bit, yeah. And so that's why there are 3 sig figs in our answer. And this is an exact value, so they're infinity sig figs. They're infinity sig figs in 12. In this 12, the 12 that is telling you how many hydrogens are in glucose. Okay, and lastly, we know there are 6 oxygens. So 6 times the oxygen. So it's going to be 6 times 16.0 grams per mole. And that's going to give you 96. Hope I'm right there. I did that in my head. Grams per mole. I didn't really do it in my head. I kind of memorized that, I think. And again, 3 sig figs, 3 sig figs, infinity sig figs. Where'd my calculator go? There it is. I want to double check that before I move on. 6 16s is 96. I got lucky. Okay. Now, we're going to add these together. Sum is going to give us the molar mass of glucose. So we just put these in our calculator, and we'll talk about sig figs afterwards. So 72.0, which is just 72 as far as your calculator is concerned, and 96. It gives us 180. Now, we look, and when we're adding things using sig figs, if we're adding, we need to line up the decimal places carefully, and they weren't very carefully lined up here. And since adding is kind of a rule we don't use so often, to be honest, with significant figures, we usually use the multiplication one. I'm just going to go over the reasoning here. Okay, so when we add all these together, we get 180, and until we round anything, we get infinity sig figs. And now we're going to start rounding. So anything to the right of these 2 zeros is going to not be any good, because the 10th place is the last digit place of significance for the carbon and the oxygen. But for the hydrogen, the last digit of significance is actually this 2, which means actually we have to discard everything that is to the right here, meaning we have these 3 sig figs as a result, coming all the way down to the ones place that the hydrogen had. So we need to demonstrate that the 0 is significant, because right now that kind of looks like there's 2 significant figures. So to imply that the 0 is significant, we would change that to scientific notation. As 1.80 times 10 to the 2 grams per mole. And that is our final answer. All right, moving on. Question 2 is a little bit more your bread and butter sort of molar mass question. What is the mass of 3 moles of glucose? So if you've got 3 moles on a scale, 3 handfuls of glucose, how much does it weigh? That's what this question asks. So we can treat as given that we know the molar mass of oxygen. Glucose. Glucose, and that's 1.80 times 10 to the 2 grams per mole. We know that for sure. All right. What else do we know? Well, we look back at the question. We know we have 3 moles, or handfuls, of glucose. We have 3 moles, handfuls, of glucose. Okay, and we want to know how much does it weigh. What's required is what's the mass. So how much does 3 moles of glucose weigh? Or rather, what's its mass? But in chemistry, we get to treat those as really roughly the same thing. All right. So what should we do? We should always start with the thing. Oh, 3.00, sorry, 0.00, 0.00. We should always start with the thing that is specific to the question. Now, this is always the molar mass of glucose. We use that as a conversion factor, not as a place to go or a place to get to, or to come from. So if we're not sure where to go, we have a sheet that can help us make some choices, right? So we've made a molar conversion sheet, or we're constructing one, and we're a few conversions in. And I'm just going to focus it again. So what this allows us to do is put our finger on where we're beginning. What do we know about our substance? Do we know how many molecules there are of glucose? Do we know how many moles there are of glucose? Or do we know how much it weighs? Well, if we look at the question again, we're asked for the mass of 3.00 moles of glucose. So what we know is we have 3.00 moles of glucose. We want to get to the mass, which is over here. And so to get there, we're going to use this conversion factor, molar mass over moles, grams over moles. So we're going to multiply by the molar mass. And that's a helpful tool we can use in order to decide what our path is. So we're going to come back to this and maybe talk about how to use this to help us trace our paths as we go. But let's take that lesson to heart. So we're going to always start with the thing we're given. So 3.00 moles, handfuls, right? And I'm going to multiply that by the molar mass of glucose, which is 1.80 times 10 to the 2 grams for every 1 mole. And I'm going to take a second to grab my red crossing out pen and cross out the units of moles. And that's going to leave me with units of grams, because mass is measured in grams. So I'll just do the multiplication here. 3 times, and that's 180, but I can type in a scientific notation just to remind us of how to do that. 1.8 times 10 to the power of 2. That's 540. Now, again, I'm going to have 3 sig figs here, so 540 grams. 3 sig figs, 3 sig figs. This should have 3 sig fig answers, so that becomes 5.40 times 10 to the 2 grams. That's how much 3 handfuls of glucose weighs. Okay, let's move on. So here we have a question about benzene, which is a common it's a common poisonous molecule. You can find it in most chemical stores. All right, so what do we know? Well, benzene rings are stable and carbonous, or poisonous, and they're carbon chain. They're a carbon ring, actually. So first thing we want to know is what's the molar mass of benzene? This is kind of similar to the molar mass of glucose. So I'm going to kind of run through part A pretty quickly. So to find the molar mass, we know we have 6 times carbons. And we already know that the molar mass of carbon is 12.0, so 6 times 12.0 grams per mole. That's going to give us 72.0 grams per mole. And we have 6 hydrogens. We have 6 times H, so it's going to give us 6 times 1.0 grams per mole. That's going to give us 6.0 grams per mole. So we're going to add those together, and we're using our adding rule for sig figs. So that means we're going to keep that place because it's significant for both numbers, and we're going to get 78.0 grams per mole. Now, this is a situation where we increase the amount of precision from the hydrogen based on an addition principle. And that's because of the nature of the value we're adding it to. Anyway, so there's a molar mass of benzene. Molar mass of benzene. All right, cool. Let's move on. We want to know what's the mass of 4,456,000,000 benzene molecules in nanograms. All right. That maybe seems kind of hard. So where do we start? Well, where are we beginning on this sheet, right? That could be a useful guide. So where are we starting? We're starting with some number of things. We know we have 4 billion molecules. And we want to know the mass. So to answer that, we're going to have to travel to moles. And to do that, we're going to do this conversion factor. We're going to perform this conversion, multiplying in this way to cancel out units of molecules and get moles. And then we're going to try and turn from moles into mass using molar mass, which we found in part A. So that's the way we're going to trace our path here. So we start by listing the thing we know. 4,456,000,000 benzene molecules. Okay. And we're going to turn that into moles. You know what? I think I'd rather try and fit this all in one line. So I'm going to try to write a little smaller so I don't have to spread this out onto 2 lines, because I think things start to get a little messy with these conversions if you try and do them in multiple lines. So 4,560,000,000 molecules is where we're starting. And like our conversion factor says, we're going to multiply to go move in this direction toward the mole by 1 mole, or 6.02 times 10 to the 23 molecules. So we get 1 mole over 6.02 times 10 to the 23 molecules of benzene. And that cancels out units of molecules. And now we know we could find how many moles of benzene we have. Okay, and now that we're in moles, we want to go turn this into mass. So we're going to multiply it by the molar mass in grams per mole. And so the next conversion factors we're going to multiply by 78.0 grams for every 1 mole. And that has the effect of canceling out units of moles, meaning we're left with grams. Well, we don't want units of grams, so we want units of nanograms. Okay, well, there's a couple things. But first of all, we know that the nanogram, this n means times 10 to the power of -9. And you may want to go back to a multicolored spectrum we made of what all of these little metric prefixes mean. So that's one thing we could do. So that means that a nanogram really means 10 to the power of -9 grams. And so I can use that fact to construct a conversion factor. Now I want units of nanograms at the end, because that's what we were asked for here. You'll remember, we want the units in nanograms. So some number of nanograms. And so some people have been using as a guiding force the fact that our final unit we want, nanograms, should be up top here. And how many nanograms? This many nanograms. 1 nanogram is the same thing as 10 to the power of -9 grams. And that has the effect of canceling out units of grams diagonally, leaving units of nanograms. All right, so let's see what happens when we punch all this into a calculator. We've got a long string of things. 4, 4, 5, 6, 1, 2, 3, 4, 5, 6 zeros. And I'll get that out of the glare. I'll try and multiply it by, I'm just going to multiply the top numbers at first. Times 1, times 78, times 1. I don't really need to multiply by 1. I'm just doing it in this case, just for fun. All right, and now I'm going to divide by the numbers on the bottom. 5 by 6.02 times 10 to the 23. And then I'm going to divide by 10 to the power of -9. And there we go. We get our answer. Our answer is, oh, I wonder how many sig figs this is. Let's go back to our question. Looks like this number had 4 sig figs, and the molar mass had 3 sig figs. And so that's 4, 3, 3, infinity, because this is a defined value. So we're going to round this to 3 sig figs. So it's going to be 5.77 times 10 to the -4 nanograms, or 0.000577 nanograms. Either one of those is fine. All right, let's move on. Question 4. We have a protocol. Now, okay, this is the most common reason why we would want to know how to use molar mass. A chemical situation is going to require 0.03 moles of a substance. In this case, it's calcium hydroxide. We want to know how much we should weigh out. How much should we weigh on a scale? So wait, what does a scale weigh? Well, a scale weighs, that's right, a scale weighs grams. So, just fold this in half here. All right, so question 4. Very important type of question to be able to answer. We know we have 0.03 moles of calcium hydroxide. Great. And we want to know what mass we should weigh out. Okay. Well, if we know how many moles we have, and we want to get to the number of grams of calcium hydroxide, well, to do that I'm going to need to do some sort of conversion factor. So let's find out how we do that. Well, let's look at our little handy heart of a mole conversion sheet. So what do we know? We know moles, right? We know how many moles of calcium hydroxide we need. So we're going to start here. And we want to know how much we need to measure out. So we're going to need to multiply by the molar mass of calcium hydroxide. Okay, so let's find the molar mass of calcium hydroxide. All right, now to do that I'm going to have to list, well, how many calciums are there? There's 1 calcium. So that's going to, where's my periodic table here? What's calcium's molar mass? It's 40.1 grams for every mole. Now, this bracket means actually there's 2 hydroxides. So there's 2 oxygens and there's 2 hydrogens. So we've got 2 oxygens, and that's going to be 32.0 grams per mole. And there's also 2 hydrogens. So 2.0 grams per mole. All right, so it looks like each of these are going to give us a measure down to the tenths, so the tenths are going to be significant. I'll add here 0 plus 2 plus 2 is 4. All right, that's going to give us 74.1 grams per mole. And remember, we found the molar mass, so we could convert mass into a number of grams, the mass. Okay. So what we're going to do is we're going to set up our expression here, 0.03 moles of calcium hydroxide. And we're going to multiply it by, remember, we're going to use this sheet, we're going to multiply to go from moles to mass by the molar mass in grams over 1 mole. So the molar mass is 74.1 grams for every 1 mole. So moles cancel out, and we're left with grams. That's going to give us 0.03 times 4.1. 2.223. Now, how many sig figs should I be expressing? Well, there's the 3 sig figs here for the molar mass, but there's only 1 expressed here. This is 1 sig fig. These guys just separate our number from the decimal. So this is not a very precise measure. So we should express that really as just 2 grams of calcium hydroxide. And we round off the other values. We round them down to 0. All right. So let's move on. The next question is about Tom. He has a steel ring. It's a 4.95 gram steel ring, and if you ask to see it, he'll show it to you, but then he'll also tell you that actually it's not steel. It's tungsten carbide. All right, so we know that Tom has a 4.95 grams of steel. Now, what's steel? There's no element that is steel on the periodic table. There is no steel. You can look, and if you can't find an element, what you can do is you can flip over to the next page, which lists all the elements in alphabetical order. And you look and you say, okay, well, silver, sodium, strontium. Wait, we skipped steel. That's because steel is not an element. It's what's called an alloy. An alloy is when you have a mixture of metals. So what do we have here? Steel is mostly iron. Wait, hang on. Does this qualify as an alloy if it's not a metal, it's carbon? Metallurgy is not my expertise. So it's got a little bit of carbon. But we're going to ignore the carbon because it's a very small amount. So we're going to imagine this is 4.95 grams of steel, pardon me, of iron. And we want to know how many atoms of iron does Tom's ring contain? So that's what we want to know. So we know we have 4.95 grams. We want to know how many iron atoms is there. Okay, so looking on our conversion sheet, we're in a situation where we start with mass. We know it's like 4.95 grams or something like that. So we're going to travel along this path to turn our expression into a number of moles. How many moles of iron? It's 4.95 grams. And then we're going to travel up to here to find the number of molecules by multiplying by the Avogadro's number of things. All right. So we can actually do that directly, I'd say. So we're going to multiply by 1 mole of iron. I'm going to write Fe over the molar mass of iron. What's the molar mass of iron? Well, I can look here, and rather than look on the periodic table, I can just look down for iron. It's in alphabetic order. Say it was 55.8 grams for every mole. That's 55.8 grams. of iron. Now that's fine. That's going to cancel out grams of iron, leave me with moles of iron. And now I need to get to a number of things, a number of molecules in this case. So I'm going to multiply by 6.02 times 10 to the 23 molecules in a single mole. 0.2 times 10 to the 23 molecules of iron for every 1 mole or handful of iron. All right. And so that should tell us the number of, or sorry, not molecules, really, we're looking for atoms. So rather than be a bunch of bound things together, we're really just individual atoms we're looking at. All right, so it's going to be 4.95. We're going to multiply it by 6.02 times 10 to the 23, and we're going to divide it by 55.8. And we get 3 sig figs worth of iron atoms. So 5.34 times 10 to the 22 iron atoms. All right. So I'm going to try to talk our way through the next one without using that mole conversion sheet, because I would say sometimes it's important to do that. All right, so what do we know? We know we've got gold, a gold bar, 12.4 kilogram gold bar. We want to know how many moles of gold. All right, so I'm going to model how we would solve this without using that little cheat sheet. That's pretty helpful. We should know how to do it, but we should also learn how to solve these questions without. Right. I'm going to drink a sip of water here for a second. Give me a sec. All right. So what I'm going to do is I'm going to start by listing things that are given. All right, I want to know the number of moles of gold in a 12.4 kilogram bar. So what do I know? I know that 12.4 kilograms are equal to 1 gold bar. Okay. I also know something about kilograms because I know I've been dealing with grams a lot. We deal with grams when we find out how many moles. So maybe I'll also write down that I know there's 1,000 grams in 1 kilogram. And that's defined. And if I need the number of moles, I'm probably going to need, if I want to convert from mass into moles, I need the molar mass. So I'll look on my periodic table, and I'll find gold. And gold is one of those elements that has a funny name and symbol, rather. It's a AU. And we can see it's 197.0 grams for every mole. So we know 197.0 grams of gold is equal to 1 mole of gold. All right. The question is, how many moles do we have? All right. So we start with the thing we know we got, right? Let's start with the most local value. So this is always true about a kilogram. This is always true about gold. And this is specific. This is specific to our problem. We got 12.4 grams of gold. So I can start by just writing down, 12.4 kilograms is what I meant to say, kilograms of gold. And I eventually want to get down to moles of gold. And we need some number of moles of gold. So we got to convert this to something. And let's look in our given section, and well, I can convert kilograms into what? I can convert into gold bars. That's fine, but that's not really a unit that's helpful to me. So maybe I should go in the other direction. I can convert it into grams. So I'll say 1,000 grams is equal to 1 kilogram. And I know I put the kilograms on the bottom because I want the kilograms to cancel out, because grams can be useful in converting things into moles. So then I can say, okay, well, I know that I can put grams down here. I want grams of gold to turn to moles of gold. So I'll put moles of gold up here, and down here will be grams of gold. This, of course, yeah. So, but how many? Well, 197.0. And how many moles? Well, 1 mole. Okay. So then I can see grams also cancel out. We're going to end up with moles of gold when we're done. Okay, and that's what we were looking for, right? We were asked to find how many moles of gold there are in a 12.4 kilogram bar. So 12.4 times 1,000 minus 0 times 1, and then we're going to divide by 197. It's going to be 62.9 moles of gold. 62.9. Oh wait, do I have the right number of sig figs? I just wrote down 3 just out of habit, because 3 is sort of a good rule of thumb for practice problems. Oh yeah, 3 here, infinity here, 4 sig figs here. So 3 was the right number of sig figs to round to. All right, let's try to wrap this up. So our last question involves Kiera. She's making some soap. Protocol requires 0.45 moles of stearic acid, C18H36O2. That's a fatty acid. And the question is, how much stearic acid should she weigh out if she wants to make soap? Okay. So this is a question where we know that we have 0.45 moles of, we'll call it SA, stearic acid. We know that stearic acid has 18 carbons. We know it has 36 hydrogens, and we know it has 2 oxygens. I'm going to put an X there. All right, what else do we know? We can figure out, okay, well, if I know the number of moles, I want to know how much you should weigh out. So what does that mean, weigh out? How do you weigh things? You weigh things on a scale. That's mass. So implicitly in this question, we're asking how much should somebody weigh out. We're really asking what the mass is. You know how many moles you have or you need, and you want to find the mass. This is a very common type of question. So you need to multiply by molar mass over a mole. So in order to do that, we define the molar mass of stearic acid. Stearic acid. Now I know it's a saturated fatty acid, so it makes me wonder if stearic acid has anything to do with the name steer, which is like a kind of cow, I guess, right? And I think of cows when I think of saturated fats. All right, so 18 carbons would be 18 times the molar mass of carbon, and that's 12.0 grams per mole. This is the carbons, and it's going to give us whatever 18 times 12 is. I don't know what that is. 216 grams per mole. That'll be 3 sig figs. And for the hydrogens, we'll have 36 times hydrogen's molar mass is 1.0 grams per mole. It's going to be 36 grams per mole. And then oxygen, it's going to have 2 oxygens, it's going to be 32. So 2 times 16.0 grams per mole, it's going to be 32.0 grams per mole. I'm going to add those together. 216 plus 36 plus 32, get 284. And when we do the sig figs, we realize we're really only accurate in the 10th place, and that extra, pardon me, the 1th place, and that extra 10th place didn't matter because only one of our values was accurate in the 10th place. So we're going to actually just round that to 284 grams per mole. And that's the molar mass of stearic acid. It's quite a large molecule. All right. And so again, we want to remember, if we know how many moles we have, we want to multiply by molar mass to turn it into a mass so we can weigh it out. And that's a kind of everyday sort of chemistry goal. So we want to be able to weigh out the right amount of things. So we have 0.45 moles of stearic acid. And we're going to multiply to turn into a number of grams. We're going to cancel out moles, stearic acid, and we're going to get grams of stearic acid. And we know that in this conversion factor, there's 284 grams for every 1 mole of stearic acid. And our moles of stearic acid cancel out, and that's going to tell us we're going to have 284 times 0.45, 127.8, which I'm going to round because there's 2 sig figs, it looks like, with the stearic acid, but I'm going to double check my original question. And it looks like there are just 2 sig figs there, so we're going to round this to 130 grams stearic acid. All right. Well, let me know if you have any questions about this. Otherwise, good luck studying.